Thank you. Hi, everybody. My name is Ahmad, as Ahmad said. I would like to thank XFEL for organizing this workshop. Also, my particular thanks to Russell Fong for setting up this work.
You need to speak up.
Yes, okay. So the title is obvious. I plan to cover these topics. I will give you a short introduction, and then I will talk about Wigner Diffraction in the presence of icosahedral symmetry. Then we will do together a manifold embedding of simulated data, and we try to recover the orientations from diffraction patterns using the manifold approach. And hopefully, if time allows, I will go to the experimental data and discuss about the problems and the solutions or the correction for such data. And finally, one slide of summary. So this slide, in fact, summarizes my talk. We have an ensemble of diffraction patterns with random orientations. We have to find the orientations in some methods, and after that, we assemble these diffraction patterns based on the orientations we have found, and to transfer from the diffraction space or Fourier space to the real space, we have to do a phasing, and then we find the object. In the case of experimental data, these data needs to be corrected. They are full of artifacts. And for this part, there are several methods. We will So, as I said, there are several methods here. I list a few of them. The GTM method, which works without symmetry, I mean symmetry of the object. EMC also has been shown that it's the same as GTM. It also works without symmetry. And angular correlation method, symmetry is essential. And I think Lana will talk about that this afternoon. Correlation maximization has worked without symmetry, and no report about symmetry application yet. And the manifold approach works with and without symmetry. Without symmetry, Peter has done some work a few years ago, and with symmetry, it's just basically the current work. So let's go to the first part. I will develop the algorithm and to see how we can get the orientation out from diffusion map approach. As you know, the rotation in SO3 can be described by Wigner Diffraction. And Wigner Diffraction contain the orientation information. They can be described by a set of Euler angles. So this is a Laplace-Beltrami operator. They are eigenfunctions of Laplace-Beltrami operator with these eigenvalues. This is the eigenvalue of the rotating top. So the L1, which is not shown here maybe. Yes, I don't know why. So there are two parameters here related to the size of 2L, 1 over 2L. 2L1, in fact, L1. This is not 2, this is L.
I see.
L1, L1, L3. And these are related to the size of the rotating top. And these are quantum numbers, J1, in the case of SO3 with magnetic numbers M rounds from -1 to +1. So as I said, these functions contain the information. So we have to work with these functions. So what about the case of symmetry? When we have symmetry, we can use SO3, but we have to symmetrize in some way the Wigner Diffraction. The object we will talk about is this virus. It contains icosahedral symmetries. And the icosahedral group, as listed here, contains 60 symmetry elements. And each element is represented by a set of Euler angle. And in other words, if we rotate the object in a certain reference frame, with this Euler angle, the object, no changes will happen. So the ordinary Wigner Diffraction in SO3 should be symmetrized in order to use the icosahedral group, icosahedral symmetry. So in general, any function of fx it can be symmetrized in this way, and this is the symmetry operation. This is a function. G, capital G is just a group, and G little g is just the element of the symmetry group, and the n is just the number of symmetries. So we have to incorporate all symmetries and then make an average. So this should be the case also for our purpose, to symmetrize Wigner D function. So instead of f, we have d, and then we have symmetrized D function. And this O operation, symmetry operation, is just come from, again, Wigner D function, because we are discussing with symmetries, and symmetries are represented by Euler angles, and we are dealing also with orientation or rotation. So we have to use, again, D function to describe this operator. So we put this operator based on, Wigner D functions here, and then separate this part and name it as a symmetry matrix. So then we can symmetrize according to this equation. For icosahedral group, J starts from 0 and then jumps to 6, then 10, 12, etc. For 0, J0, S matrix is just 0. The first non-zero S matrix comes from J6, and this is sufficient for us to describe the symmetry of the object. So with M6, we will have, with J6, we will have 13 M values starting from -6 to +6, and this means that we will have a matrix of 13 by 13 dimension, totally 169 elements, but fortunately, most of these elements are 0, and we are just facing with 9 non-zero elements. So this is the matrix. We apply this matrix on D function. D function also has its own elements. This is in fact D matrix. And then after symmetrization, here we do something else. We do, let's say we use a unitary transformation in order to diagonalize S matrix, and then use the eigenvectors of that unitary matrix to symmetrize D function. I didn't go to too much details about that, but in any case, after the symmetrization, what remains is just 39 elements, but among them, just 13 elements are independent. So we work with those 13 elements of symmetrized D function, and they are shown here. J is 6, and then M runs from -6 to +6. So we will have one singlet for M0, and then 6 degenerate pairs. So to have an idea about Wigner D functions symmetrized, of course, this is the general formula of them. And it starts from 5 because the first row and the last row, also the first column and the last column were 0. Okay, so now we have symmetrized Wigner D function at hand. Let's try to see what are the eigenvalues. If we put it again in the Laplace-Beltrami operator, in other words, if we apply the Laplace-Beltrami operator on the symmetrized Wigner D functions, we can easily observe that the eigenvalues do not change. So we have the same eigenvalues of the symmetric form. And here we have 7, let's say, eigenvalues because we have 6 degenerate pairs and 1 singlet. Okay? In reality, and in the case of diffusion map, we are facing with real eigenvectors. And here we have to make real value of the D function because they are complex. So this is the way we use, and you have seen it in quantum mechanics too. Okay, now let's try to see how they look like. These are scatter plots of Wigner D functions. I just used 5,000 random Euler angles and put into the Wigner D function, and these are just scatter plots of those using those Euler angles. So each point here, in fact, is one set of Euler angles, or accordingly, each point will be one diffraction pattern in the case of diffusion. So this just gives you an idea. Sure.
You calculated from a icosahedral object diffraction patterns. What is this?
Here, still, I have not done anything with diffraction pattern. I've just used some random values of Euler angles to have an idea how they look like. Because we will see them from diffusion.
But they follow icosahedral symmetry.
Exactly, because they are already symmetrized. Oops. So, okay. Whose copy was this? almost. Almost. It's all right. Okay. Let's go. Now we have symmetrized D function. Let's go to the diffusion map and see how the results look like. So we used two cases. We generated some simulated diffraction patterns from this virus, satellite electrosis virus, with two different resolutions. For 2 angstrom resolution, 1.3 million data points, and for 6.6 angstrom resolution, we generated 80,000 diffraction patterns. The size of this virus is 20 nanometers. Okay, let's do an embedding together, and we put diffraction patterns here into the machine of diffusion map, and we get the manifold. Every data point here is just one diffraction pattern. So one diffraction pattern will be 1 point here. Okay, I don't go to too much details of that. So after embedding, we have at least, we should consider 13 eigenvectors, because we had 13 symmetrized Wigner D functions, but we cannot show them in 13-dimensional space. So we just project them onto different combinations of psi I, psi j, psi k, as shown here. But in fact, 3 dimensions are useless for us. We work with 2D scatter plots, 2D representation and 2D projection with them. And in fact, psi 1, psi 2, psi 3, as Peter mentioned, there are Wigner D functions. Okay, now let's see the similarity between Wigner D functions and results from diffusion map. This is one of the generated pairs from diffusion map. This is corresponding one from Wigner D function, and you can see the similarity well. And likewise for the eigenvalues. So we have 6 degenerate pairs here. Likewise for the Wigner D function, for the diffusion map, and 1 single, and single here. For the diffusion map, the eigenvectors can move. So necessarily they are not in the same order. You will see that in the next slide. So a few remarks. We need enough number of diffraction patterns depending on the resolution. Otherwise, the degenerate pairs will not be quite round. So we have to use enough number of diffraction patterns to fill up the space somehow. So sign of eigenvectors is arbitrary, like in the case of, let's say, any eigenvalue problem. And eigenvectors are not ordered the same as Wigner D functions. Again, we have a common problem in the eigenvalue equation. And degenerate pairs can rotate independently with different speeds. These notes should be, let's say, taken in mind, and then we will use them for the alignment. These are from diffusion map, and these are from Wigner D functions. As you see, this is psi 1, psi 2 related to M6, related to M5, and so on. But they are not necessarily in the same order as a D function. For instance, I have 1, 2, 3, 4, 5, 6, then I have 9, 10, 11, 12, 16, 17. So I have to go to, let's say, the eigenfunctions and see which are similar to the D function, and then use them for the fit and for the alignment. So this is a typical degenerate pair from diffusion map and the corresponding Wigner D functions from symmetrized Icosahedral D function. They are not necessarily in the same, let's say, order, and we have to say that, I have to say that every D function is just a combination, a linear combination of these two. And you will see that the reason in the next slide, because this can rotate compared with this frame here. So every D will be a combination of psi 1, psi 2, or vice versa. And the psi should be normalized according to this. This is by dividing by the square root of 13, which comes from the orthogonality of the Wigner D functions. So this was the rotation I was talking about. This is the rotation I was talking about. So D6 and D-6 is plotted here. The corresponding pair from diffusion map is rotated. It can be arbitrary angle here. So therefore, we can see that C1, C2, C, or C2, C1, they are just, in fact, sine and cosine functions. This is just a 2D rotation matrix. So we can use this 2D rotation metric to bring the manifold degenerate pair back to the Wigner functions in the same direction.
But you have to determine theta, right?
Exactly. I'll briefly talk about how to do that. So in order to make the theta angle, we use we use this operation. In fact, we mirror, let's say just one typical diffraction pattern. We have it. We mirror that image according to the horizontal axis, and this mirroring, in fact, is equivalent to this operation here, Wigner D functions. So you can see that in the case of D functions, we have the original diffraction pattern here and the conjugate pair, or the mirror pair is just here. So in the case of diffusion map, it's not just exactly the horizontal axis. It has been rotated already. So we put that rotated diffraction pattern into the data and just do embedding, and after that we track that conjugate diffraction pattern and the original one. And the bisector of those will show a deviation from the horizontal axis. So this just gives us the theta angle. Yeah. What about the orientation? Any degenerate pair can rotate clockwise or counterclockwise. So we have also to find this to make a valid fitting. So for this purpose, we slightly rotate one diffraction pattern. I'm just talking about one diffraction pattern, but in fact we do it in several and then do our averaging. But let's just take original diffraction pattern here and just rotate it around the beam axis slightly by 3 degrees, for instance. After putting that into the diffusion map, we can see the rotated image is here or is here. Then we can identify whether it has rotated clockwise or counterclockwise. Then here we find a sense of rotation of the degenerate pair. And we have to fit it to the Wigner D function, because 3 of the degenerate pairs for the Wigner D functions rotate clockwise and 3 of them counterclockwise. So we have to match these together. If it is not rotated in the same way of the Wigner D function, we have to change the sign of eigenvectors to make it the same sense, or the same direction. Okay, now we have the Icosahedral D functions here. We have everything. We have done a visual assignment. We have matched the degenerate pairs. Now we are ready to do a fit. So we have a 13-dimensional cost function. So for each D function and psi1, psi2, as you remember, I said it's just a combination, linear combination of that. We can write down a cost function. And for 13 D functions, we have 13 cost functions. So we will do a fit in 13-dimensional space, a nonlinear least square fitting. And after this, we find out the Euler angles for each data point. Okay. So now we have the orientation, we have the diffraction pattern. So we can assemble this diffraction pattern based on found orientation. Okay, the input is 2D diffraction patterns, and we found orientation, and the output is the diffraction volume. So according to the orientation, we just assemble this diffraction patterns, and use an interpolation in order to make the diffraction volume. We use the so-called congruent for this purpose. And this is what we got from the lower resolution. This was the, let's say, something like diffraction volume, and then we did a phasing, and this was the wires we found from manifold embedding, and using 80,000 diffraction patterns. And the resolution is just 6.6. And this is the known structure as a PDD file, so we can see that they are pretty close to each other. But we didn't stop here. We use also 200 resolution elements in the wires, and we were able to find even the atomic resolution of these wires using 1.3 million diffraction data.
So just 100.
100 resolution elements, sorry. Yeah, 200 was just the size of the diameter of the object. Okay, now let's go to the experimental data. Experimental data are just gorgeous. As you see, we have everything other than single particle. So I just forgot to put the percentage of diffraction, single particle diffraction data, but about 10% of the whole hits are just single particles. But within that single particles, we have a lot of problems we see. So this is aggregated diffraction pattern. This is multiple hits. This is maybe a blank shot. These two are maybe single particle hits. One of them has strong scattering, one of them weak scattering, and so on. These data were taken 3 years ago by this group at LCLS, and they used water jets. So experimental data, what problems we are facing with? We have shot-to-shot intensity variation. We have nonlinear detector response. We have water jet scattering in the case of using water jet liquid jet. We have multiple hits in the data. We have background electronic noise. We have beam movements, and we have sample heterogeneity, and so on. So for a reliable 3D reconstruction, we need to minimize these effects as much as possible. Okay, this is a typical diffraction pattern I showed you a few slides ago, 2 slides ago. There are some stochastic effects. A and B come from injector, scattering from injector. C and D come from maybe water jet. E, as you can see, some parallel lines on the background. They are coming from electronic noise, and so on. These are just a few of them. So let's embed them. Again, for the experimental data, what you get is just this one. But in the case of simulated data, we work with this one, the ideal case here. Now the main task is somehow we have to convert this one to this one if we want to find orientation out. Okay, so each artifact somehow plays its own role here. For instance, if I remove the area of water jet, apply a logic gap here, you can see the dimension of manifold just collapses to a 1D. The whole manifold just collapses to 1D manifold. It will be a kind of row. But still, it's just a parabola. For the simplicity, we use this one because this is easier for sorting data. Another example of variation, this was the manifold. And if we compute the total intensity of each diffraction pattern sorted along this manifold, we can see this intensity plateau. And as you see, the intensity varies from a maximum to a minimum, meaning that intensity varies from end of this parabola to the end, to the other end. So we have to get rid of that somehow. So how to do that? We have worked with a few scenarios. We have done intensity variance normalization of the data. We have developed a dynamic flat fielding. Also, we have used NLSA, nonlinear Laplacian spectral analysis. And we have also used standard SVD. So here I will focus in these two, and you will see the results. So the flat fielding. The traditional flat fielding methods reduce variations in detector response, and they are just one-time correction for all data. But here, in the case of XFEL, stochastic effects changes from shot to shot. So this means that we require a different flat field for each diffraction pattern.
Could you explain what a flat field correction is?
Well,
what are you correcting for?
From a, let's say, background, from a stochastic effects, from something other than signal.
You're basically making sure that all the pixels have a uniform response.
Yes.
Right? So you're correcting the pixel response to the image.
Exactly. That's right. So, I mean, this is in more detail in the next slide, actually. So, for a perfect detector, with a uniform response during the experiment, what we can see is after averaging over all diffraction patterns will be something like this. We have, let's say, perfect rings with each QX. This is from, I think, RDV data, simulated data, and I use 10,000 diffraction patterns here. So snapshot orientations have equal probability. These are, in fact, the principles we will use to make it flat fit. And so all snapshots in the perfect case, they have equal probability orientation from orientation point of view. And also the average of the snapshots should be azimuthally uniform. Like here. This is noise free. This is just perfect simulation data. But in the case of experiment, if we do average, what we get is just this. We don't see any ring of perfect, any azimuthal symmetry here. You can see this stuff here, this stuff, these dark ones here, and so on. So we have to somehow convert this to the previous slide.
Photoshop.
The easiest.
He thought about that.
Okay, I just tried once, so that's the second. It doesn't matter. Doesn't matter. So how we use manifold? So we had this manifold, and this is the pipeline like that. So we sort the data according to this manifold from here to here. We fit the problem to this and find the arc length, and then sort the data according to the arc length is that problem. And then we divide the sorted data into some intervals. For instance, from T1 to Tn, or Tn here. And a local flat field for each T, or tau, in fact, tau interval is just generated. And also we just combine all intervals together and make a global flat field. And then we normalize the raw data by these flat field factors and see what happens. So this is the idea. Comes from the principle I talked about. So this is the raw data, original data, and they have ns number of diffraction patterns. We divide the data of the problem to n interval, and then for each interval we find a flat field, and then for each interval that flat field is multiplied by the data, and then we have corrected data in that interval. So the idea of flat fielding is coming from here. I mean, the normalization factor is just generated as here, as you see here. So we just make an average, azimuthal average of the diffraction pattern, and then also the average of total diffraction pattern without making any azimuthal averaging in that interval, and then this is the normalization factor. In order to see how it works, let's put this flat field again to this and see if corrected I is just independent of phi or not. This is the goal, to make I independent of phi, just as a function of Q. So if we put this flat field here and just do the follow this procedure here, at the end we will see the I corrected, or let's say corrected I in tau interval will be independent of phi. This means that we have applied azimuthal symmetry on the data.
So if this is not diffraction data and say E and gauge space images, what would be the parameter that you would check with?
I mean, which problem? I mean,
So
compared to which problem?
For diffraction data, you can make the assumption that okay, it should be phi invariant in
Yes.
the range, but if it was an E and image and you're correcting,
I believe the same principle holds.
Well, I can answer that. Actually, try on it is actually not easier because their cameras are already flatly corrected prior to the experiment. And further, the dynamic range is extremely small rather than the XFEL, so you don't have this non-linearity issue.
Also background statistics.
Yeah, you can measure it from essentially from a uniform illumination.
Okay, so this is a raw diffraction pattern in a typical tau interval, and this is the flat field of that interval. If we multiply the flat field of that interval to the raw snapshot, we get a flat field of data. As you see, this, let's say, tau has been removed from the corrected data, and if we average over flat fielded data, we can see azimuthal symmetry. Although it works somehow well, but we were not happy about that because maybe some backgrounds or additive factors, we couldn't get the manifold that we are looking for. So that's why we went to the second approach, SVD. So for the SVD, briefly, I would like to say that we project the data, the supervector of the data onto the manifolds. X is a supervector, concatenated version of the data, and the psi are diffusion map eigenvectors, and mu is just a Riemannian measure of the manifold. And on the other hand, when we have the A matrix, we can do SVD, standard SVD on that, and it will be something like this. We have n number of SVD modes here, and these two are in fact equivalent, this part and this part. And then we can, from here, we can reconstruct the data from SVD modes. If we use all modes, we get back the original data. However, if we get rid of some artifact modes, we can maybe get some corrected version of data. This is what we do here. So this is, again, the same summation as before, but we remove some artifact modes. I will show you the next slide what do I mean by artifact modes, and then we add just the good SVD modes and reconstruct the data. And we can do it even without projecting into Manifold, and we can use it even with the standard SVD.
I see. So that embedding it first is not necessary.
I mean, we tried it actually, but I mean, this works much better than this. But I mean, the manifold helps.
So there's something linear, and the non-linearity
depends on the data, maybe. Can say that. But actually, it depends on how many modes, how many dimensions of the manifold we consider. Just changes to different factors. Okay, so let's do a standard SVD with the data, the same data I showed before with data, and these are SVD eigenmodes. So you can see, for instance, this is just a kind of artifact mode. These are good because we see symmetries, with the symmetry in them. This is, for instance, an artifact. You can see some stuff here, and likewise for the others. So we can just remove this artifact modes from the SVD modes and then do a reconstruction. And what we get after that is just this result here. So the original data was this manifold, and the corrected data by SVD just rid of these variations here. We get this nice degenerate pair here, which is comparable to the simulated one. Unfortunately, we need one more degenerate pair to do reconstruction, and we are looking for that. But in the last summer at Elsevier, they did an amazing experiment. We just stopped this work for the moment, and currently we are working with that data. And I would like to say that we have some fantastic results will be available to public hopefully in the near future. So this is the bulk of my presentation, and finally, I mean, I will summarize my talk in these 4 lines. Manifold method is able to extract high resolution 3D structure at very low signal to noise ratio. On the other hand, XFEL snapshots are dominated by artifacts, which varies from shot to shot. Manifold-based algorithms can reduce stochastic artifacts. And finally, if we would like to find a reliable 3-dimensional structure out of data, we have to somehow correct this data and use any approach we have. Thank you very much. This was the